Hi, my name is Aditya and I am the CEO of Automatski. Automatski makes the most powerful quantum simulators, annealers and computers in the world. Today I am going to demonstrate our quantum circuit simulators to you, and I will keep it extremely short. I assume you already know the theory and the applications, and I also assume Automatski has given you the context of this video. So you will understand what I am going to show you. If you receive this video by mistake and don't know what this is all about, just ignore it. I'm here to tell you what we have achieved and not how we have achieved it. All our millennium breakthroughs are completely our own inventions without absolutely any collaboration or help from anyone else. All the implementation details of all our inventions will be a secret for the next 1,000 years. If that doesn't work for you, then you can stop watching this video. Okay, now this is basically quantum circuit. It is a generic oracle, and basically I tell people that the easiest way to test a quantum simulator or computer is to test it through oracular problems. Oracles are used to model all classical problems of interest that we want to solve, almost all, and especially NP hard problems. And now the other thing you can do is you can reverse engineer problem definitions from solutions, and then you can use those problems to test and benchmark quantum simulators and quantum computers. Now this is a test environment. Our hardware setup is basically a test setup, so it is working at 1,000 times slower speeds, and it is not perfectly accurate. uh, a production environment will be 1,000 times faster and 100% accurate. This is a full state vector simulator, so it is not an approximation. It is not a density matrix formulation or a tensor matrix formulation, etc. Tensor matrices don't work anyway for problems of interest. They only work for shallow, really shallow problems. So this is a full state vector, and it is available in configurations from 50 qubit configurations to 300 qubit configurations. Now, nobody in the world has been able to simulate quantum systems, quantum computers with more than 50 odd qubits, because simulating a quantum computer with 3940 qubits takes a GPU cluster, which one of the vendors in the world is very famous for doing. People have tried simulating quantum computers with around 4950 qubits using the world's topmost supercomputers, but beyond that, it is not possible outside Automatski. So Automatski is the only company in the world which sells quantum circuit simulators with 300 plus qubit configurations, and these can be used for production grade problems like catalysis, nitrogen fixation, carbon capture, battery design, drug discovery, etc. Now, all our quantum systems are hosted remotely in our data centers, and they are offered over a remote API, and they have bindings for various programming languages like Java, Python, Rust, or Mojo or whatever. So that is not an issue at all. This is Java. This is the Eclipse environment, and here I'll explain the first problem to you and skim through the problem definitions for the other problems. So this is a generic oracle problem. I have a secret number which I'll keep changing in multiple executions. For example, this is 9. I will convert it into a bit sequence, which is 1110. Sorry, it is not 1110. 1110 is 2, 4, 6, and 8. Sorry. So that is not 9. Now I have connected to a quantum simulator which is of big capacity, and I have various gates defined here, and I start executing those gates on qubits, and I increment a gate counter, how many gates I have executed, because I also want to see how fast this execution is going, how many gates are there, etc. And then I prepare the qubit states. I have an oracle in the middle of the circuit here which encodes this secret number inside the circuit, and then I post process the oracle outcomes, and then I do the measurement. Here you see that the measurement does not have include something called the number of samples, because our quantum systems work in deterministic mode. Both our quantum simulators and our quantum computers also. We just say that these are the indexes of the qubits I want to measure and give me the top end results, and it will give you the results and you can plot a histogram, etc. This is the status function that will print the status periodically. So that's about it. This is a standard quantum circuit, very transformable to any quantum system you want to execute it on, because it is built from the fundamental building blocks, which are quantum gates. So you can take a program in built for some other quantum system at the level of gates and convert it into this, and vice versa. So so this is 9. The secret is 9. Let me run this circuit here. So this is the bit sequence. This means 1 and this means 8. So it is 9. And you can see it is perfectly deterministic, 100% accurate. It is a full state vector simulation. All 100% results give you 1001 combination. Okay. Now if I change this combination to 6, let me change it to 5. See this, the first one is 1 and the second one on the third place is basically 4, so it is 5. So this is one of the best ways to test the accuracy of a quantum circuit. Our quantum circuit simulator also simulates noise channels. It simulates non-linear quantum gates, which can be used to solve NP-hard problems. In fact, that is the only practical way of solving NP-hard problems. Oracles don't work for problems of sizes of interest to us. So let us see a financial application here. Here is a very long circuit. Like I said, it is built from the gate level up. So it is a complicated circuit, and it is doing an options pricing. And this is from a research paper, and it will draw the plot, etc. So I'm not going to explain the circuit to you, which I can't anyway. It is very raw. So here is the quantum circuit, and here is the most optimum options pricing at 110, whatever that means in financial terms. Now if you look at this problem, this is a simulation of a artificial life protocol. If you know how diseases spread, etc. Artificial life protocol is like that. I spread a disease to you, you die with 20% probability, you spread it to others, and so on and so forth. So a lot of complicated quantum gates and computations, and then again I print the results. Now we have also, Automatski has also done large scale, massively large scale quantum gravity simulations, and that is a very interesting problem, but we'll discuss it some other day. So here I am going to run this artificial life protocol, and you see this is a survivor of 0110. This is a survivor, everybody else dies. Now how do we benchmark our systems? So do we benchmark against others? There is simply no way for us to benchmark against others, because nobody can keep up with the scale and accuracy of our systems. So we need a way to benchmark the speed and accuracy, etc. Accuracy I've already shown you. Let us benchmark it for speed. So I'm going to run 100 gates for each configuration of 20 qubits, 26 qubits, 28, 30, 32, 36, 40, 45, 50 and 57. Okay. And I'm going to start the quantum simulator for each of those qubit configurations. I have a random set of 1, 2 and 3 qubit circuits, and I'm going to print out the performance benchmarks. Now let me run this. Remember, this is a test environment, and our test quantum system is not as accurate as the production system, and 1,000 times slower and 1,000 times cheaper. We set up our test systems just so that we can demonstrate our solutions to everyone without spending millions of dollars in creating a production grade quantum system. which all of Automatski's quantum systems, simulators, annealers, etc., are custom built to order with a lead time, hosted in our data centers and offered as a remote service. Now you can see here the 20 qubit system performed at 34 gates per second and used up 0.12 gigabytes of memory. The 28 qubit system performed at 13 gates per second or zero point zero 0.07 seconds per gate and took 1.9 GB. So this is all coming from the quantum system. So I'll let it complete. Why did I choose 57? Because a lot of vendors in the world claim that they have built quantum systems with 57 qubits and done random sampling on it, and no classical system can match it. So we just want to say that we can do a full state vector simulation of 57 qubits. Actually we do to 300 approximately. So just for that reason I mentioned 57 here. This will take a couple of more seconds. Let it complete. 45 qubit configuration benchmarking has been completed, and so the timing and the results depend on the circuit also. There is a slight dependence, but the worst case is what we can manage with our quantum systems. I'll just let it complete. Yeah, that's the reason 50 qubit configuration ran at 1 gate per second. That is why it took 100 seconds. So, but I really wanted to, and 57 qubit ran at 7 gates per second. So this is how the benchmarking, we benchmark our systems for scale and performance using oracular systems. Thank you very much. That's all we had to show you today. If you have any questions, you can email us at info@automatski.com.